Alright, let's continue with what polyphase definitions. So what is polyphase? Circuit or system in which AC source operate at the same frequency but different phases are known as polyphase. So same frequency, for example, we do have 50 Hz applicable or application in Malaysia. So, but with different phases. So we, for example, three phases. We have the red, yellow, and blue. So phase A, phase B, and phase C. So this is for instance, for example. So this is known as polyphase. So the need of polyphase electrical supply. So earliest application of AC current was for heating the filament of an electric lamp. So for this purpose, so single phase system was quite satisfactory. So this is how it begins. So it starts with the invention of a bulb, where the inventor back then so create a filament, they heat it up for this electric lamp or bulb, and finally the single phase system was widely applied. Then some years later, so AC motors were developed. So what is interesting part of this AC motor? So nothing compared to the single induction motor, where the type most commonly used so was not self-starting unless it was fitted with an auxiliary winding. So some auxiliary or some additional winding is necessary in order to make this AC motor, or namely induction motor, more interesting. All right. And then so it was found that by using two separate windings with currents differing in phase by 90 degrees, or with current differing in phase by 120 degrees, so the induction motor became self-starting, had better efficiency and power factor. So this is the more interesting part of the motor, all right, the AC motor, for example. So they come up with these two separate windings instead of one single winding, and try to apply currents, certain level or certain amount of currents with different phase and 90-degree apart or 120-degree apart. So they figure out that the motor is now become a self-starting machine with better efficiency and power factor. So what happened if they apply into a generator? All right. So employing two 90 degrees, especially this phase winding, is referred to as a two-phase generator. Then utilizing three 120-degree displaced windings is referred to as a three-phase generator. So after they've invent an AC motor, especially this induction motor, with two separate windings, now they come up with a better idea of employing two 90-degree displaced windings, and the result is more interesting because the generator is now able to generate higher energy with better power capacity. And then the two-phase voltage generations. So two-phase electricity is produced by having an alternator with two sets of coil, one 90 degree apart. So see figure. So this is the figure of simplified diagram of a two-phase alternator. So we have phase A as well as phase B. So just now in earlier slide, so we have seen one coil with one single phase, all right? But this time around we have two phases, namely phase A and phase B. So similarly, the waveform over here, so the waveform generated for phase A as well as phase B. So it's now the voltage of a two-phase system, therefore 90 degree out of phase with each other. So these two out of phase voltage can produce a rotating magnetic field. So we can see now the phase A is being generated, as well as phase B. So these two waveform is separated by 90-degree apart. All right, because if you look at the design, okay, the physical design of the coil, so it is actually again separated by 90 degree. So this is in vertical position, all right, phase B, and horizontal position for phase A. Okay, so for this again, for these two coils, so it generates two different type, two similar type of waveform, but they are separated by we call it the phase in degree. Okay. All right. Again, so V1 and V2 from the previous slide. So we have V1 with this equation E max sine omega t. Okay, so we can simply say that V1 is equal to E max with say 0 degree. All right, and then the second voltage E max sine omega t minus 90 degree because it comes later or it lags behind. So we assign it as minus 90 degree, or we can simply write that second voltage V2 from phase B, for example, so is equal to E max 90 minus or negative 90 degree. So usually circuit use 4 wires, okay? 2 for each phase. Less frequently, 3 wires were used with a common wire with a larger diameter conductor. So this is how to simplify the 4 wires for 2 phase. So because we are talking about 2 phase, V1 and V2, but they still require 4 wires system. All right, but less frequently, 3 wires were used with a common wire with a larger diameter conductor. Even though we reduce the number of 4 wire, all right, into down to 3 wires, but it still require a larger diameter conductor. So what happened to current century? So 2-phase power was superseded with 3 phases and is not used in the industry. So meaning the 2-phase, all right. So the 2-phase method over here, so is now has been obsoleted and okay, upgrade to 3-phase voltage generation. So this is the most interesting, the most important part of the study. All right. So why we need 3-phase system? So a 3-phase generator so has 3 separate pairs of coils on the stator. So each specially separated from the other 2 by 120 degrees. So this is when we deal with the balance system. So we have 3 separate pairs of coil which is separated way by 120 degree each. So the 3 coils form 3-phase generators. So we have seen that one single coil generate one single waveform. So 2 uh, coils generate 2 phase waveform, and then now comes to 3 coils which generate or form 3 single phase generator. So the voltage induced in each coil is equal in amplitude. So the peak, so you can see the peaks, they are all equal. All right. So with the voltage in the other 2 coils, but differ in phase from each other by 120 degree. This means from red to green, and then green to blue. So they are differ in phase by 120 degree. So large 3-phase generators use an electromagnet instead of a permanent magnet in their rotors. So this is in terms of the design. Okay, this one. So the design, the physical design of the machine itself or the generator itself. So they use electromagnet instead of permanent magnet. So this means they require another different type of winding or coil instead of permanent magnet. All right. So this you learn in detail when you come to machine course or machine subject. So this is the YouTube. You can see yourself and I will upload this link or this YouTube video in your Google Classroom. So the generator three-phase output over here. Okay, this is the output terminal, and where we can see the waveform. All right, so this is the physical construction of the machine, for example. So the reference come from T. Davis 2002. So all the coil, all the winding, you can clearly seen or represent in blue color, all right, red color and green color, or the notation A, or notation of A, notation B, as well C. All right. So at the end of the joint, at the end of the coil is one single joint over here. So this is the neutral point. All right. And then, okay, if you have what they call it, oscilloscope, just for example, so one simple oscilloscope, so you can simply see the sinusoidal waveform for each pair of coil, A, all right, B as C. So this is for A, the blue color, right, and then this is for B, red color, and this is for C, the green color. Okay. So again, you may refer to this link and read it yourself, how the function of AC generator frequency. So the generated voltage VR, Vy, Vb. So this is the notation stands for rate. So this is the voltage, generated voltage stands for Y phase, and this is generated voltage for blue phase. So are known as phase voltages. So if VR is chosen as the reference voltage, so let's say VR is your reference. All right. So then the phasor forms of the three sinusoids are as follow. So this is your reference voltage, reference neutral voltage. So we can simply write that VR, this is equal to Vm sine omega t, or in simple form, we can write VR equal to Vm with with zero angle. All right. So why zero? Because it becomes our reference. Then when it come to second phase, the Vy, sorry about the color. So I just want to make it difference. The Y is actually stand for yellow. Okay, then the second one, so we have this equation. So Vm sine omega t minus 120 degree, because it is generated 120 degree phase after the first generation of VR waveform. Okay, so we have Vy in simpler form, Vy equal to Vm minus 120 degree. So where Vm is the peak value of the phase voltage. So Vm stands for maximum voltage. All right. So and then the third one, similarly, we could simply understand that another waveform so will be produced, and we can simply write the equation, which is Vb equal to Vm plus 120 degree, or actually in the original form, this is actually negative 220 degree after VR. All right, so this comes minus 240 after VR. Okay, I repeat, if you go back to Vy, so this is 120 degree after VR, right? But for Vb, so this is minus 240 degree after VR, or in the other way, you can simply say this is actually 1 plus or positive 120 degree ahead of VR. Okay, in the same position actually. Minus 20 after VR or lag behind VR. This is equal to positive or plus 120 ahead VR. All right. So activity, so just complete it yourself. Draw the phasor diagram of VR, VY, and VB. Okay. So what makes these three different is the position. Okay, of the position of the phase. Okay, we have R, we have Y, as well as SB. All right. So this is 120-degree apart. All right. So another 120-degree apart. Similarly, this is 120-degree apart. All right. So this is R. So R is 120-degree away from R. Okay. Or we can simply say this is negative. And then B also same. So we have negative 120 from Y, but from R here to here, this is minus 240. All right. Or similarly, this is actually 100 plus 120. Okay. The VR is actually 120 plus VB. Okay. All right. Now, so each coil of the three-phase generator can be connected to one of three identical loads. So assume we have three similar or three identical loads over here, Z, theta. So each coil of three generator can be, so this three can be actually connected. So this way, the system will consist of three separate single circuit differing in phase angle by 120 degree. Okay. And then three-phase Y system. So alternatively, the negative ground ends of the three-phase generators, all right, and loads can be tied together to form a common return line, which is called neutral. Okay, so the system form is known as a four-wire Y system. So remember, for neutral, all right, for neutral line, okay, this is actually applicable only for Y. Okay, so there is for delta, so there is no neutral. So delta there is no neutral because for neutral is defined here, common return line. This means there is one common return line. All right, from this R, for example, this is Y, so this is B. So these two ends, so coil R, these two ends for coil Y, and these two ends for coil B can be connected at one common line, this one, so return line. So we call it, this is as N. But for this one, so there are 3 points over here, and not any point which is commonly connected, somewhere here or somewhere here, somewhere. So this is impossible. So meaning, so no neutral for data. All right, as simple as that. Okay, this is the drawing, the diagram for four-wire Y system. So R, V, Y, for example. So this is another Y. So we have the load. So this is the generation supply. All right, so this is the load. So in between, change the color first. So in between, so we have red color. All right, over here. So this is for neutral. So notes Y configuration is sometimes called the star configuration. So Y also, this is, we can simply call Y. we can simply call as star. And then the outgoing lines are called line or phase conductor. So this is the outgoing, the red one. So this is the outgoing. So the outgoing. So we simply call this is as line. All right. This is simply called line or phase conductor. So line voltage are voltage between lines, either at the generator or at the load. So between this and this, all right, this and this. Okay.